Hello, everyone, and welcome to today's webinar, Quality Assurance in the Hematology Laboratory, presented by Sten Westgard, Director of Client Services and Technology, Westgard Quality Control. I am Alexis Corrales of LabRoots, and I'll be your moderator for today's event. Today's educational web seminar is presented by LabRoots and brought to you by Abbott Diagnostics. To learn more, please visit abbott.com. Now, let's get started. Before we begin, I would like to remind everyone that this event is interactive. We encourage you to participate by submitting as many questions as you want at any time you want during the presentation. To do so, simply type them into the Ask a Question box and click Send. We'll answer as many questions as we have time for at the end of the presentation. If you have trouble seeing or hearing the presentation, click on the Support tab found at the top right of the presentation window, or report your problem by clicking on the Ask a Question box located on the far left of your screen. I now present today's speaker, Mr. Sten Westgard. Sten Westgard is the Director of Client Services and Technology for Westgard Quality Control. Mr. Westgard earned his MS degree in computer science from Pace University, New York, New York. For more than 20 years, Sten has managed the Westgard website, course portal, and blog, creating and administering online training, as well as editing and writing hundreds of reports, essays, and applications on quality control, method validation, Six Sigma risk management, and other laboratory management topics. For a complete biography on our speaker, please visit the Biography tab at the top of your screen. Then, you may now begin your presentation.
All right, thank you for that kind introduction, and welcome to today's HIT series sponsored by Abbott Diagnostics. The HIT series are hematology and hemostasis webinars and live presentations designed to help Abbott's customers learn more about innovations and clinical approaches that can support their laboratory's goal in achieving measurably better healthcare performance. My name is Sten Westgard, and today's topic is quality assurance in the hematology laboratory. I want to begin, of course, with a standard disclosure that Abbott Laboratories is supporting my time and my presentation. There is a more unorthodox disclosure that I should make, and that is particularly for those of you attending a webinar, you need to understand which Westgard you are hearing from. There are two Westgards, but you may only be familiar with the first Westgard. I am known simply as a Westgard, whereas my father is known as the Westgard. So if you have heard of the Westgard Rules, those are a creation of my father, and I, as you, have been following them for the last 30 years. I have only about 25 years in this field, whereas my father is actually celebrating his 50th year of contribution to laboratory medicine. And what we do in addition to training, we provide a series of resources through the internet to laboratories worldwide. We have Westgard.com, a membership site that has more than 59,000 laboratory professionals. It's a free membership, and if you join, you get access to more than 600 different articles, essays, lessons, and so forth that have to do with quality control. We have a course portal where we do structured training, and we have a blog where we cover shorter articles, things in the news, and most importantly, questions and answers. The agenda for today's webinar starts with a review of our current QC practices in hematology. After we do a review, we'll look at some frequently asked questions and frequently flouted recommendations when it comes to QC in the hematology field. And we'll even look more closely at how common poor quality control practices are in the hematology area. And then we'll suggest a solution, a next generation of quality control practices, which combine the power of the Westgard Rules with the power of Six Sigma and introduce the ability to actually determine quantitatively your QC frequency. When we talk about hematology in the laboratory, there are a number of papers that have come out in the last decade that have called into question the level of quality that's being delivered. So for instance, this paper in 2010 was stating that many of today's QC procedures are nonspecific in hematology, and they lead to non-productive practices, which is incongruous with the fact that we have very advanced engineering and some analyzers in hematology that are in their 4th or 5th generation. And another study that came out in 2012, looking at just basophil count, found that 3 of the instruments out of 3, so 100% of the methods that they looked at, were providing unsatisfactory quality, low correlation between the basophil count of different instruments, between instruments, and according to the reference method. And this can be, of course, something that is not just important to the laboratory in terms of its own ability to stay in quality control, but this can go out and really impact patients in a dramatic fashion. So in a 2009 study, looking at the platelet measurements methods of 3 different automated hematology analyzers, the study found that under-transfusion was observed with the use of all of the analyzers that were studied. And of course, under-transfusion can be a big problem for patient care. So we have papers going back a decade that suggest quality is not quite as given or as reliable in hematology analyzers as we expect, or definitely as we would wish. Then there are some other questions that come up when people adapt what we might call the traditional QC approach from clinical chemistry to the special conditions of hematology analyzers. So some of the questions that we frequently get on the Westgard website are, can I just use the manufacturer's mean and standard deviation when it comes to quality control in hematology? Can I simply use the manufacturer's provided controls? Can I just use the control ranges that are provided on that package insert? Do I have to use the Westgard rules in hematology QC, or should I avoid them? And then a very specific question for hematology is, our controls have such a short lifespan, isn't it too hard or too difficult to establish the actual mean and SD for those controls? When it comes to talking about the manufacturer's mean and standard deviation, we refer to ISO 15189, and the technical requirement states specifically, the laboratory must design internal QC systems that verify the attainment of the intended quality of results. And that design means you have to choose the control rules, the numbers of control, and the frequency. You have to verify that the performance is acceptable, and you're trying to meet some level of intended quality. And that intended quality usually is in the form of an analytical performance specification. Using the manufacturer's controls is not recommended by ISO 15189. Instead, they recommend using third-party independent controls. And that's just the latest version of ISO 15189 where that recommendation was added. And typically, ISO 15189 document watchers will notice that if something is recommended in this version and it's an optional recommendation, that's a sign that the next version will probably make it a mandatory requirement. So independent third-party controls becoming a mandatory requirement of any ISO 15189 laboratory, that is the future that we are headed toward. The reason that even a document standard like ISO 15189 recommends this third-party control, it's because there's too much evidence that manufacturer controls get tweaked or adjusted or manipulated, and that the control lot becomes synchronized to a new reagent lot, and that results in a loss of the objective ability to detect shifts and changes in clinically important errors. I like to tell people that when you use a manufacturer control, sometimes what's happening is the manufacturer is controlling you. In chemistry, we have a very well-recognized problem of this, where these manufacturer controls are not very sensitive to real errors. And that's why in best practice documents for the chemistry field, it's very well stated the best practice for laboratories is to have third-party independent controls. can I just use the manufacturer control ranges? Well, here we can look at a CLSI document, H26, and this is the second accepted version. And this is a standard, or I should say a guideline, that lists the best practices for hematology quality assurance. And in that, CLSI says the laboratory must establish its own expected mean and QC values of recovered control values. Published manufacturer ranges are typically too broad for effective QC. And the problem that happens when you use a manufacturer's range is your limits will typically be spread very wide from the mean, and it will make your limits look very permissible, and it'll compress your data very, very close to the mean. It'll give you an illusion that everything is in control, when in fact you may be effectively practicing blind man QC. You're missing errors that are clinically important, but the way you've constructed the Levy-Jennings control chart makes it appear as if everything is fine. Another frequently asked question is, should I avoid using the Westgard rules in hematology? This often comes about when we're talking about manufacturer ranges and 2 standard deviation control limits, and there's a particular issue when you use the full set of Westgard multi-rules on hematology QC charts, particularly the 10x rule. Now, the CLSI guideline says multi-rule analysis, which means Westgard rules, it's strongly recommended. And it also notes that decisions based solely on plus or minus 2 standard deviations are too simplistic and they are insufficient. And then they quote Westgard, and here again they're probably quoting the Westgard, not myself, a Westgard. The traditional use of 1-2S warning control rule is no longer recommended. And instead, the recommendation is a hierarchical selection of specific multi-rules that maximize PED, where PED stands for error detection, and minimize PFR is recommended, using Six Sigma and power function approaches. That one sentence is alluding to some advanced techniques that we'll be introducing in the later part of this webinar. But essentially, it's saying don't use the 2S rule and look at your Westgard rules, but don't use them on everything. Don't use all the Westgard rules on every parameter, but instead shape the approach, shape the number of rules you're going to use based on the performance of the method, based on the needs of your patient. And how you'll determine what the best fit is by analyzing the different rule sets and seeing which gives you the highest error detection, or PED, but also minimizes your false rejection, or your PFR. And again, the way that you'll do that is by applying Six Sigma approaches. Our final question is about, isn't it just too hard to establish the mean and standard deviation when my controls have such a short lifespan? And this is a chronic problem for all hematology labs, where if you get 1 month of stability, that may be typical. You're lucky if you get 2 months of stability out of your hematology quality control. So by the time you've established or collected 20 data points, which is usually the minimum to establish your own mean and standard deviation, you're almost at the end of the lifespan of that control. So one solution is to do an overlap of controls. So as the previous control lot is ending, then you start the new control lot 3 to 5 days ahead of time, and during those 3 to 5 days you make multiple measurements, and so you collect that 20 data points in advance, so by the time the last lot actually finishes, you're ready with a new mean and a new standard deviation. You can perform the switch over to the new quality control lot, and you actually have enough data to keep going. If you don't like that long of an overlap, another solution is to use just 8 overlapped values. So that is, you have the new control lot, and you run 8 controls, and from that you just calculate the new mean. There is a rule of thumb that 8 values is enough to reliably establish a new mean. It's not reliable enough to establish your new standard deviation. But if you have the new mean, you can use the old coefficient of variation and make a temporary set of new control limits. And you can see the equation right there. It's the new mean times the old CV, and that gives you a temporary standard deviation, and you can use that on a temporary basis to draw your control limits. And you should only use those temporary control limits just long enough to actually accumulate those 20 data points so you can get the new mean, you can get the new standard deviation. And then that way you'll have the new mean, the new standard deviation, you'll have all the correct data to properly create your control charts. Now, a third solution is to use a cumulative mean and standard deviation from multiple control lots. And if we look at the C24 guideline from chemistry, they say 3 to 6 months cumulative values for mean and standard deviation. They give you a reliable, stable, consistent specification for mean and standard deviation. For solutions 2 and 3, we are making an assumption that there's not a lot of difference between each lot of hematology controls. So if you see that there is a big difference between each lot of hematology controls, solutions 2 and solutions 3 are probably not appropriate because you're going to get, you have two different performances, and then if you try and average those together or cobble those together to give you temporary control limits, they're not really giving you something that reflects the real performance of either. So that brings us to the end of the frequently asked questions. And now we're going to look at how common poor quality control practices are in hematology. We did a survey in 2016. We got responses from over 900 labs from more than 100 countries. Now, to be fair, most of the responses were from chemistry labs. But of those responses, we got about 100 of them that were from hematology laboratories or laboratories that shared their hematology QC practices with us. So we can delve closely into just how frequent problems are in the hematology sphere. And we can see in the first question that about 70%, just under 70% of labs state that they are using 2 standard deviation limits for their hematology QC. Now this is in contrast to what we see in chemistry, where it's only about 55%. So this is an antiquated practice. 2 standard deviations is about 50 years old. When labs were just starting to do quality control, they used 2 SD limits. Everything else in the lab, of course, has changed, but we seem to be burdened by this legacy of history this tradition of using 2 standard deviations. The biggest problem with 2 standard deviations is that it can give you a 5%, 9%, or a 14% expected false rejection rate, depending on whether you're running 1, 2, or 3 controls per run. If you have something as high as a 14% false rejection rate, you are spending most of your time chasing ghosts. These are problems that you don't need to be chasing down. They don't actually represent a real problem. So this is a technique you should abandon. We also see that about 70% of labs are using Westgard rules for some tests, and that's almost in line with chemistry. In chemistry, it's a bit higher. About 78% of the time, chemistry labs are using Westgard rules. And of course, the benefit of these Westgard rules is that they maximize your error detection but minimize your false rejection. So they still give you the error detection that you might like to have, that the 2 SD limits used to give you, but they don't have those false rejection problems from the 2 SD limits. Instead of 14% false rejection, you're down at like 1% or 2% or at most 3% false rejection rate. When labs are choosing their control ranges, you can see there's 2 main ways in this chart that 56% of labs report they use the manufacturer's range. So that is the most common way laboratories set up their QC is they just use the manufacturer's range. So that thing that we told them they shouldn't be doing, that's what they're doing most of the time. But just behind that, 53% of labs also report they will actually calculate the mean and standard deviation. This is in line with what we see in chemistry as well, although in chemistry we see that more labs choose their own mean and standard deviation, do their own work, than use the manufacturer's range. So hematology is a little bit behind in moving away from manufacturer ranges when compared to chemistry. When we look at the type of controls that hematology labs are using, nearly 80% of labs are just using the manufacturer's controls, and this is much higher than what we see in clinical chemistry, where it's only about 2/3. About 30% of labs are using third-party liquid assay controls, and that's a little bit lower than what we see in chemistry, where that number is 37%. One interesting finding is this average of normals QC, or what some people call patient data QC, or what you may know as Bull's algorithm. Almost a quarter of labs in hematology are using that type of technique, that patient data-based QC. That's much higher than what we see in chemistry. It's half that. It's only about 12% of labs in chemistry using that technique. And that technique is very powerful and very useful, so this is an area where hematology is really the leading area of the laboratory and when it comes to patient QC. How often do labs run their QC? 41% of labs in hematology are just running it once a day. That's a little bit lower than what we see in chemistry. In chemistry, it's 47%. The other number that we see that's pretty different is almost a quarter of labs are running 3 times a day, or probably once a shift. That's almost twice what we see in chemistry. So in chemistry, it's much more fixed that it's once a day QC, whereas hematology, partly due to regulations, is often encouraged to run QC more than once a day. And what happens when laboratories in hematology have an out-of-control event? How do they troubleshoot their out-of-control event? Well, 80% of them do what we want them to do, which is to troubleshoot, to actually seek the root cause, and before they consider rerunning a control, they actually try and find the source of the problem. But more than that, 86% of labs are actually just repeating the control. They see a value that's out, and they cross their fingers and they hope that by repeating it, it will just fall back in. That number is a little bit higher than what we see in chemistry. In chemistry, less than 3/4 of labs will repeat the control. But you can also see that if the first repeated control doesn't work, there is almost 60% of labs willing to prepare and run a new control. So that is, one control is out, they repeat it, it's still out, then they run a new control. And then 20% of labs will repeat the new control if that's still not in. So essentially, they're running 4 times to hope that a value will fall back in. And this repeating and repeating and repeating response we often call gambler QC. You're just trying to roll the dice one more time and hope that the numbers come up that make it appear like you're back in. How often is this kind of out-of-control event happening in hematology? Well, 40% of hematology laboratories report that it's happening once a day, more than once a day, or once every few days. So it's happening quite frequently. So all of these problems that we see with hematology QC, because you are having so many out-of-control events, this is really a burden to your laboratory operations. It wouldn't be so bad if, yes, we repeat controls, but we're only out of control once a month. We might be willing to accept that kind of workaround or that kind of imperfect protocol if we weren't seeing so many out-of-control results. But if we have out of control results every day or multiple times per day, then that's really telling us we are overwhelmed by outliers. We are overwhelmed by alarms. And what really we risk is we may start going deaf. We may stop listening to these alarms because we get them so often. This is a condition that's well known in clinical circles, particularly with electronic health records. When you hear about alert fatigue, that typically describes what happens when a clinician gets too many pop-up warnings. They get so many warnings they just get used to clicking them and dismissing them, and they actually will miss a very important alarm. The same thing can happen in our QC. We get so many QC alarms that we consider to be, oh, this isn't a real problem, we'll just repeat the control, it'll fall back in. But in fact, there may be a real out-of-control situation that is going to impact patients, and we miss it. We dismiss it because we think, oh, it's just another one of those false rejections. And this corrosive problem means that we get labs that will report patient specimens, will report patient results, even though their QC has told them that they are out of control. So here it's about 9% of labs will report patient results despite being out of control, daily, weekly, or monthly. And that is actually a little bit less than what we see in the chemistry. We see this happening. 1 in 10 labs are reporting results when they're out of control. And the final question that we have asked labs in this survey is, have you actually changed how you do QC? And 78% of labs in the hematology area have said, no, we've made no changes to how we run our QC. It's the same kind of QC we've been doing for the last 10 years or 20 years or 30 years. And this is higher than what we see in chemistry. In chemistry, more than 61% of labs say that they haven't made any changes, but it's not as high as 78%. So pretty much it looks like QC practices have been in a kind of stasis or status quo for quite a while, and a lot of poor habits have accumulated. Now that we've cataloged all of our problems and really explored how prevalent those problems are, we want to move on to suggesting some solutions. And just as you've probably installed or added a next-generation hematology instrument to your laboratory, we're going to introduce a next-generation type of QC. And that's going to be more than just the Westgard Rules. It's going to be Westgard Rules plus the addition of the Six Sigma technique, and then something that we've just added in the last year is the ability to determine quantitatively, scientifically, the QC frequency, just how often you need to run QC. The core of the Six Sigma approach is to benchmark your quality on this 0 to 6 scale. So there's a universally accepted scale from 0 to 6 on the Sigma performance benchmark. And Six Sigma is world-class performance, and that is less than 4 defects per million reportables. So if you have 1 million test results and you're at Six Sigma, then less than 4 of those results are expected to be defective or in error or to be false positives or false negatives. This is essentially almost defect-free. And what you'll find is if you are at Six Sigma, your laboratory operations become more efficient, your test results become more effective because your clinician knows and is very confident that those results are reliable and accurate. The other end of the Sigma scale is typically considered 3 Sigma. That is, the minimum acceptable performance is 3 Sigma. And that corresponds to about 67,000 defects per million reportables. And outside of healthcare, if you're at 3 Sigma or lower, industry and manufacturers would be thinking about radically improving or redesigning or even replacing any process that has performance that problematic. a 3 sigma or a 2 sigma process really consumes too much time and money and effort from a laboratory or manufacturer or any kind of industrial process. You're really generating too many defects, which causes you to do more troubleshooting, to spend more time tracking down, redoing your work, having to do multiple tests to get one correct answer. It really ends up being too expensive to maintain such a low sigma process. And of course, because there are so many defects, many of those could get out and reach patients and impact them in adverse ways. When we make the application of Six Sigma to hematology, when we're talking about the analytical tests, we need a number that tells us how good each parameter needs to be. In other words, for leukocytes, how good do we have to be in order to provide accurate results and support the best patient care? There are many different sources of these quality requirements or analytical performance specifications. For instance, in this first column you see CLIA. Those are the U.S. regulations, and it directly regulates 1, 2, 3, 4, 5 different parameters. In Germany, there are the Regelbach rules, and they specify interlaboratory comparison goals for 4. There is something called the RECOS database, and the most recent version that we have available was published in 2014. And based on biologic variation studies, they can specify for almost every parameter in hematology how good you need to be as good as possible given the known variation that the body introduces to those laboratory tests. And then the final column is actually a kind of consensus statement from Spanish EQA or proficiency testing groups. They looked at the actual proficiency testing results of their member laboratories and tried to figure out what are those labs capable of achieving. They're trying to figure out if there are some goals that are so small no one can hit them, well, what's a more practical goal? What can today's technology achieve? And so out of all of those different resources, we make a recommendation for your common parameters, use the CLIA goals. For your differential counts, you're going to be using the RECOS goals, and then there are some times where you're going to want to rely on the Spanish consensus goal. Many of the RECOS goals for leukocytes and erythrocytes and hemoglobin and hematocrit, those goals are so small that really no method on the market is capable of achieving those at something like 4, 5, or 6 sigma. So maybe the next generation of instrumentation will be able to hit those goals, but it's not something that we should expect to see in the next few years. Once we have those allowable total error goals, we can then use that as the context, and we introduce our bias and our imprecision, and that allows us, you can see at the bottom of the slide, to calculate our sigma score. Our sigma metric is the allowable total error, which was on the previous slide, and then we subtract the absolute percentage bias, which we might be getting from our peer group or our EQA/PT program, or our comparison of our actual control mean versus the target mean, and then we divide that number by the imprecision, or CV, which is, of course, what we get routinely from our controls. And what you have in front of you is a Westgard sigma rules. So it's the traditional Westgard rules, but you see there are some vertical blue lines that divide the Westgard rules into different sigma zones. And so if you're at the 6 sigma zone, you'll notice that the blue line comes up, and there's really only one Westgard rule you need to use. So if you have a 6 sigma hematology method, you don't really need all the Westgard rules. You can set your limits at 1/3s, or 3 standard deviations from the mean. And then if you look lower, below that 6 sigma number, it gives you an estimated run size, and it says 1,000 patient samples. Well, that means every 1,000 patient samples, you should probably run QC. That's the way to minimize the risk of impacting even one patient result with a clinically significant error. And then as you look across horizontally, as you go to 5 sigma, that run size drops to about 450. 4 sigma, it drops to 200, and 3 sigma, it drops to 45. So you can see that as you have more more sigma, you do QC less frequently with fewer rules. But as your sigma goes lower, you will need more Westgard rules, and you will need to run more frequently. So your life gets harder the lower your sigma gets. Just to conclude, I want to give you this message that we really need to make improvements in how QC is practiced in hematology. There are many common counterproductive practices in the field right now, and we should be moving away from those. Manufacturer controls, manufacturer ranges, and interference, that should be avoided, and we should be moving towards your own mean, your own standard deviation, and third-party independent controls. And if you have 6 sigma performance, or 5 sigma, or even 4 sigma, you will get some real benefits by applying this more advanced technique of combining Westgard rules with 6 sigma and then modifying your QC frequency. We see in chemistry, and we expect to see in hematology soon as we apply this in labs around the world, that those 6 sigma parameters, they get financial benefits from the reduction of the number of Westgard rules that are implemented, from the reduction in the number of controls that need to be run, and really you'll see a reduction in the number of outliers that are flagged by your system, because there are many flags that you might think were errors that now will not be clinically significant. You will not consider them to be real errors. You might see a 10x, but if your method is 4, 5, or 6 sigma, that 10x violation actually is not that important. And for hematology, that's a really good thing, because that 10x is probably one of the most common errors or common problems that they see as the controls reach the end of their lifespan. They begin to drift and shift, and now we have a way to say that shift might happen, but we're not going to have to worry that we need to reject the run because of it. We have a way to adjust ourselves because we know so much about the performance of the method. And with that, I want to conclude this part of the presentation, and I want to open it up to questions. So now, if you haven't already submitted a question, I would love to take your questions and have a dialogue about other issues you see in hematology QC. Thank you very much.
Thank you, Sten, for your informative presentation. We will now start the live Q&A portion of the webinar. If you have a question you'd like to ask, please do so now. Just click on the Answer a Question box located on the far left of your screen. We'll answer as many questions as we have time for. So let's get started. Our first question is, the difference between lots. Can we assess the difference between lots using vendor-provided values as the basis?
That's a very good question, and I think this is a question that not only pertains to hematology, but really every discipline within the laboratory. And the most recent recommendations on lot-to-lot changes and assessing them really push the important decision-making tools onto patient samples. So it's not that you want to use what's in the package insert. That's really a vague guideline. What you want to do is take, sometimes it's 10 patient samples from the previous lot that have already been tested, and then you retest them on the new reagent lot, and you compare the differences in those two results. And if those differences exceed what you've defined as a critical difference, then you now have an evidence-based observation that the new reagent lot is significantly different. And significant, usually you set that difference to be something that's almost clinically significant. And at that point, if you have that signal, you start thinking about the manufacturer of the reagent, and you see, is there a fix that can be made to that reagent, or is there a different reagent that could be provided that would be more appropriate? And when they say a critical difference, that can be more easily understood as it's going to be a fraction of the allowable total error. So we're pretty familiar with allowable total errors. We can figure out maybe it's going to be a half, maybe it's going to be a third of that allowable total error. That's considered an acceptable bias in between the two reagent lots. And if it exceeds that 1/2 to 1/3 of the allowable total error, then you're really shifting the values too high.
Now, Sten, you suggested eliminating the 1-2s rule, but for a 2-2s failure, it requires both to be out. Doesn't that make both runs suspect?
Well, I guess I would make a distinction between what is a 1-2s rule and a 2-2s rule. So a 1-2s rule is, as we would define it, it's a single value outside 2 standard deviations. And again, the problem with that is most of the time when that happens, there's absolutely nothing wrong with the method. It's simply a false rejection. And the false rejection rate with one control is around 5%. With 2 controls, it's just under 10%. With 3 controls, it's around 14%. So a 14% false rejection rate ends up being just really overwhelming to a system. Now, the 2-2s rule, that is a good rule, that when necessary, if you have 2 values that are outside 2 standard deviations on the same side, that's not going to happen very often, and when it does happen, it's going to indicate a problem. So we're not suggesting eliminating the 2-2s rule. That's one that should be in your arsenal of QC techniques. But the 1-2s rule, that's really a half-century old, and it's antiquated, and we should be moving on to something that's more advanced.
Manufacturer-provided upper and lower limits are already very narrow. For example, plus or minus 0.5 difference from the mean for hemoglobin. Can we use these cutoffs?
It's interesting that in many cases, the manufacturer's range is often complained of as too wide, not too narrow. And remember that the manufacturer's range, it's built on the variation of many, many laboratories. So typically the problem is there's so much variation in all the laboratories that they sampled that your range is, your standard deviation is quite large, and therefore your manufacturer range is quite wide, and it would be wider than what you see in any individual laboratory. So typically the manufacturer's range is really only supposed to give you a beginning helpful idea of this is somewhere within this range your actual mean should fall. You should find your actual mean within this manufacturer's range, and if you don't, then it's a signal that however you're operating, you're outside the expectation of all the other labs. The manufacturer's range is not meant to be your QC range. They're not meant that you write them down as, oh, these are my control limits, and I'm going to use them for the rest of my QC operations. In the absence of having any information at all about the performance of your control, then yes, it's a very temporary use of the manufacturer's range could be acceptable. But that would be really, if you think about it, it's when you first have an instrument and you first have that control and you have no historical information at all, that's when you would use the manufacturer's range. If you're finding that the manufacturer's range is too small, again, what you should be doing is figuring out your own range, is putting together enough data so that you know your own mean, your own standard deviation, and then you can draw your own control limits. And if your control limits are wider than the manufacturer's range, that is acceptable. That is okay. I would say it's rare that I've heard of a scenario where the manufacturer's range is tighter than the lab's actual range. But it's not, I suppose, on paper, that's not something that could not happen. It's just rare that it would happen.
Now our next question, how can 86% just repeat the control, but 80% troubleshoot appropriately? Are these the same labs?
All right, so that goes back to the question of how we were conducting our survey. And we were asking laboratories, what do you do? And we explicitly allowed for some questions multiple answers. So they could, labs could say, well, I actually do troubleshoot, but if you're thinking about your full hematology menu, we're not asking you to answer on just one test. We're saying overall, are there tests where you really do troubleshoot, or are there tests where you actually just repeat the control? So we allow the labs to answer as many times as possible. So some labs will say, yes, on some tests I do the right thing, and on other tests I do the wrong thing, where I'm just I'm doing the gambler approach to QC, and I just repeat the controls over and over and over. So that it could, we don't have the granular ability to rule out that these are different labs making those responses. But obviously, since the percentage is so high, there's a lot of labs that say, well, I do the right thing sometimes, but I also do the wrong things just as frequently.
Ladies and gentlemen, we are getting so many good questions today. So just as a reminder, we will, any questions that we do not have time for will be answered by the speaker via the contact information that you provided at the time of the registration. So Sten, let's continue. In a stable system, a 2-2S situation is expected once every 400 samplings. If this happens more than that, how can you call that a false alarm?
That's an interesting question. Again, we're getting back to the 2-2SD rule, which in our previous question we definitely did not want to rule out as a possible rule that could be used. And now we hit the idea of the expected false rejection rate, whereas what will be your observed rejection rate. So through simulation studies with any particular QC rule, we, and this was some of the pioneering work by the Westgard, was to figure out what is the expected false rejection rate of any of our particular control rules. And so we might be able to say the 2-2S rule, we would expect 1 out of 400 runs there will be a rejection. And then that, but while we might expect that it comes along once every 400 runs, in reality, the way probability works is it doesn't weight that exact amount. You might get 2 false rejections within 10 runs, and you won't know it. It's just you know, the way random things work. They don't come on a schedule. So if you see multiple 2-2S violations, it's still entirely possible that those are false rejections, and they just happen to be clustering in an unusual way. So even when we know these rates or these percentages of expected false rejection, that doesn't mean we can therefore say within a given time frame, if we see more than one of those rejections, it's either a false rejection or not a false rejection. Whenever a rejection occurs on any rule, we have to assume it's a real rejection until we can rule that possibility out, until we do the troubleshooting and say, well, none of these other things are wrong, so it looks like that particular rejection, there's no reason for it. We will therefore call it a false rejection.
Now, if you are calculating your own reference ranges and one test falls outside the manufacturer's range, how do you proceed?
Okay. Now, I think we have to. I'll make an assumption when we're saying reference range, you're meaning control range. If it was if you've truly established your own reference range, and then you have a value fall outside your reference range, that's something that might not be taken into account during your QC monitoring stage. It might be happening during the clinical interpretation stage. But let's go with the idea that you've established your own control range, but the control range is different than what you see on the manufacturer's range. And again, the manufacturer's range is giving you an idea of where your mean should lie. It's not defining how a broad range within which your control range must also fall. So you could have a mean that's still within the manufacturer's range, but then the actual control range might tip above or below where the manufacturer's range is. That is completely acceptable. So that would not be something that you would want to be concerned about. That's just the way the system has been set up.
Now, is there added value of doing QC for calculated hematology parameters like MCV, MCHC, MCH, etc.?
Those do add quite a bit of value, particularly those indices become, they're very strongly controlled and very predictable. So when you see something go wrong on an indis, that's usually a sign something's very wrong. And if we think about another use of those indices, if we think about Bull's algorithm, if we think about the use of patient values, there are some parameters in hematology that are uniquely suitable for closer monitoring of the patient values. And in fact, as I mentioned earlier, hematology labs are twice as likely to be using a kind of average of normals or moving averages or a patient data QC technique. And the benefit of that is, one of the benefits is you don't have to buy controls in order to use that technique. So it's very efficient. It's also very close to the patients. And it also is providing you a real-time monitor of the QC process. So if you think that we might have methods that are at 6 sigma, which means we actually reduce our QC frequency to quite, to once per 1,000 patients, well, in between 1,000 patients and our QC events at either end of those, it will feel comforting to everyone if we have a moving average or a patient data kind of QC that's monitoring all of those moments within the QC bracket.
Now our next question is, CLSI H26-A2 and CAP checklists speak to the relative uselessness of low-level controls in hematology. In the USA, only 2 levels are required. Would you comment on that?
So, yeah, there are not only just in hematology tests, but there are some cases in other disciplines. I might actually think about your infectious disease and your some of your screening assays, where the low-level control, it starts to reach the level of it's almost a blank. It should give you absolutely no signal at all, and it's very difficult for you to develop a good normalized distribution. One of the things that we try and take into account when we're doing Six Sigma benchmarking is choosing the best control level. And often, if it's a case where that low-level control has no utility, we will say, don't even bother calculating a sigmametric down for that level. Figure out, if there's a low positive or there's another, the middle or the high level of control is actually where you make critical medical decisions. That's where it's important to figure out the sigmametric. Now, in terms of how many control levels you need, the sigmametric response, the sigmametric calculation will help you determine just how many levels are necessary or optimal to do QC. So it could be you're running 3 levels right now, but if you find out you have a Six Sigma method, then you could look at what are the QC procedures that have just 2 levels of control, and how will they provide me enough quality control, enough error detection to adequately monitor this method, and then that will explicitly allow you to move away from a 3-level control to a 2-level control, because you can then demonstrate, well, this 2-level control and whatever control rules we set up, that provides me with enough error detection to detect any really medically important error, but I don't need a 3rd level of control to do it. So obviously you have to check your regulations, because some regulations somewhere in the world will say for hematology you need 3 levels of control regardless of the utility of those individual levels. But if, as the question suggests, in the USA 2 levels are sufficient, then you can figure there is an evidence-based way for you to move away from a 3-level control and then justify why you've gone to a 2-level control. And Sigma metrics can help you do that.
We have Abbott analyzers, Cell, DIN, Ruby, and we use controls provided for Abbott. But these controls are manufactured for Streck. Do you consider this controls as a third part control?
All right, that's a great question, because there's this very strong emphasis on having a third party or independent control, and some manufacturers will do a bundling, where they're getting a control from a third-party vendor and they're just including it with their instrument. We would count that as an independent control. Where it becomes not an independent control is where the manufacturer or the person who's providing it to you, with the instrument, has actually built the control themselves and had a hand in setting its expected value. And often, I guess, I have too many anecdotal pieces of evidence where the manufacturer's control gets tweaked, adjusted, somehow its range gets changed, so that as a new reagent lot comes out, the manufacturer's recommendations for the control lot also change. And what happens is there may be a change in the reagent lot, but the control has been adjusted so that you won't be able to detect that change. And really it comes down to incentives of the manufacturer, where since they don't make any money on the control side, all of their effort and their incentive is to minimize the number of problems and phone calls and complaints that are generated by the use of that control. And so they will typically want as wide a range as possible. And when you call in technical support, they'll say, did you run the control? Is it within our range? If it's within our range, then we say it's fine, even though we already understand that the range that they have set on is too wide. There's just they are finding ways to control their customers, not necessarily control their method.
Now, it looks like we do have time for a couple more questions. Let's keep going. How does these new rules align with regulations imposed by CLIA, by CLIA?
So the new recommendations, I suppose what we have to understand is that the CLIA regulations, which are probably some of the more specific regulations in the world, they really only require you to do some QC. They don't necessarily say, by the way, you should use these limits and these rules. So what our problem has been, I suppose, with CLIA is that they haven't been specific enough. And inspectors will simply ask effectively, an inspector in a laboratory in the U.S., they look to see if you have a chart that has lines on it and dots on it. And if you can say, yes, see this, it's a chart, it has horizontal lines, it has dots that are, all over this chart, then the inspector will say, okay, you're doing your QC job. They really don't often get down to the level of specification where they ask you, okay, I see you're doing these set of limits. Can you prove to me that that's adequate for this method? Or can you prove to me that you're detecting a medically important error with the QC procedure you've implemented on this test? They never get that specific. So these tools fill in that gap of saying, yes, I know you're doing some QC. Now let's figure out how to get you to do the right QC. And sometimes the right QC is less stringent than what you're currently doing. And in some cases, it will be the opposite. You might be using 2 standard deviation limits, and when we do an objective analysis of the test performance, we'll realize, wow, you actually need to do Westgard rules and think about increasing the frequency of how often you do QC. So we are not, these new techniques are really filling in a gray area or a gap in the regulations. So it's not that this will change how you get inspected. It's simply that you will have more confidence as you operate and as you report results.
Now, we run approximately 9,000 samples in 24 hours. Using Six Sigma, you'd have to run QC 9 times within 24 hours and use the Six Sigma. That does not seem logical for us in this size of lab. Can you comment on this?
Well, I was showing you the simplified QC frequency suggestions. If you have a Six Sigma method, you may, and you actually use what we call a Six Sigma QC frequency nomogram. So there's a much more granular tool that will give you won't give you a simplified recommendation. It'll give you a more exact recommendation. And this approach is really only 2 years old, so we're still also trying to understand the consequences and implications. It could be at a Six Sigma method, you could be going to once every 3,000 or 4,000 or 5,000 patient samples. And I think, so it's not that let's not get stuck on once per 1,000. In terms of doing the QC minimum, if you're just doing one set of QC, so you're doing 2 levels or 3 levels of control in the morning, and then you do 9,000 patient samples, and then you consider running QC again, well, we're probably going to say that may be a situation where you want to increase the QC frequency, if only because of what's the downside when you're out of control. If you go 9,000 patient samples, and then you find out you're out of control, how do you retest 9,000 samples? What is the risk to patients if we go almost 10,000 patient samples before we do any kind of check? At the very least, I would say if you've got your QC frequency down to multiple thousands in between your QC events, I would strongly recommend having those moving averages, the Bowles algorithm or the patient data QC, monitoring some of those methods so that if in real time you can see one of your patient moving averages start to dip or spike, that gives you the beginnings of a heads up on there may be an analytical problem occurring, and we need to run some controls at this moment to figure out if we're still in control or if we're not.
Now, what are your thoughts of an IQCP for hematology due to lack of variations between lot to lot?
So IQCP, this individualized quality control plan, now if we bear in mind that these really were invented to try and help justify a lunar-based QC frequency for most point-of-care devices. That is, we have point-of-care devices where they want to just run QC once a month, and they couldn't figure out a really scientific way to justify it, so they came up with a document approach, which is the individualized quality control plan. And if you put IQCP on the top of a document and then you have a table of contents that has three components, an error risk assessment, a QC plan, and a quality assessment plan, then you can make any QC frequency decision that would be reduced from once a day. The QC frequency recommendations, we tend to say the IQCP as currently structured, it uses risk analysis as cover to come up with an arbitrary decision. Because most labs that were doing once-a-month QC, they went through their IQCP, and at the end of it, they decided they were still going to do once-a-month QC. So that IQCP process really was a lot of paperwork. It wasn't a lot of science, and it wasn't a lot of judgment. Now, the approach that we're talking about QC frequency, where you actually call on the Kurt Parvin model, which looks at the maximum risk to patients, the max enough variable, that is a scientific, data-driven, reproducible way to determine your QC frequency. If you can reduce your QC frequency based on that model, which is what we incorporated into the Six Sigma QC frequency nomogram and what we put on that last slide of the Westgard Sigma rules, that's a data-driven way to reduce your QC frequency, and that would be what we would consider evidence-based and acceptable.
We have gotten so many good questions in today, and we are still getting more. We are going to wrap it up with this one right here.
Yeah.
When
so
setting up your meet, go ahead.
I would say because there are a lot of Westgard portals out there, I'm going to be copying down these questions, the ones that I didn't answer, and if you can be patient and give me a day or two, they will pop up all the questions plus some answers on one of the Westgard websites.
Perfect. When setting up your mean and SD, years ago I was informed that the new mean must be a number within the manufacturer's stated control range. Is this true?
Yes. Your mean should fall within the manufacturer's range. If your mean is falling outside the manufacturer's range, essentially they're saying, we've looked at a lot of different labs and we've come up with a range of expectations, and you're outside that range of expectations. You're significantly away from the herd. And if you think many of those recommendations tend to be instrument specific, and sometimes they could be even peer group specific, down to the same lot of reagent, then you really shouldn't be behaving so differently from the rest of your peer group or the rest of the rest of the laboratory herd. So if you do find yourself outside of that, you need to start investigating if there is a reason why you've drifted so far away.
Thank you, Sten. Do you have any final comments for our audience?
Well, I would say, I suppose this is something everybody in hematology already knows, but typically, when we talk about QC, we will say, well, each discipline will say that they're different, but most of the time they're not different. It's just a question of changing like the context or the expectation. The biggest challenge with hematology is that lifespan of controls, and that really is different than anything else we see in laboratory testing. I hope I've tried to give you some coping mechanisms for dealing with short life cycle of the controls, but it is, I think, within our power to still manage hematology parameters within the same level of quality that we see in other areas, even though we are hampered by a short lifespan of our controls. And thank you again to all of you from so many different places in the world who tuned in for this LabRoots webinar, and I hope we'll be able to do something like this again soon.
Thank you again, Sten, for your time today and your important research. We would also like to thank LabRoots and our sponsor, Abbott Diagnostics, for underwriting today's educational webcast. Before we go, I'd like to thank the audience for joining us today and for their interesting questions. We've received so many great questions today. Due to the amount of questions that we were unable to answer due to time constraints, Abbott and Sten will be sending out an email with information on where you can view these questions and answers. Don't forget, you may continue to submit questions during the on-demand period. This webcast is viewable on demand through February of 2019. LabRoots will alert you via email when it's available for replay. We encourage you to share that email with your colleagues who may have missed today's live event. Thanks again for joining us. Goodbye.